Yo, welcome to another Mr. Nutran video. We're going to cover water potential problems. Let's start off with the first warm-up problem that we had. A plant cell has a solute potential of -8 bars and a pressure potential of 2.5 bars. So right now I see that we have a cell, and then it says the cell is placed in an open beaker containing a solution with a solute potential of -5 bars. In which direction will water flow? So when solving these types of problems, I like to draw my picture and then my cell here. So in order to know how water is flowing, water will always flow from high water potential to low water potential. They have given us solute and pressure, and the general equation for water potential is pressure potential plus solute potential. And then we can specifically solve for the cell and then for that solution. So that's what I'm going to do. I'm going to use this equation here to plug it in for the cell's water potential and then take the values for the solution and do the same. So let's go ahead and solve. So we have the water potential of the cell. The pressure potential, as stated in the problem, is 2.5 bars. And then we have the solute potential at -8.0 bars. When we add that together, we get -5.5 bars. So this right here in the cell is -5.5. Now it's time for the solution. So the water potential of the solution is equal to, and when you see this keyword here in any water potential problem, open beaker means that the pressure potential is indeed 0 bars. And then plus the solute potential is -5.0 bars, giving us -5.0 bars. So that -5 goes here in our picture. And so again, water flows from high water potential to low water potential. The higher value when we're comparing negative values will always be the number closest to 0. So that -5 value is actually higher than the -5.5 according to the number line. So high to low means that the water is going from the solution into the cell. B is our answer here. Awesome. Now we have our second problem. At 20 degrees Celsius, whoa, that's the key here. For questions that involve temperature, we're always going to be using the solute potential equation. -I C R T. Okay? So when we see temperature, that should give you guys a big hint that you need to use that equation. So let's continue reading. A plant cell with a pressure potential of 3 bars is at equilibrium. Whoa. Another keyword here. At equilibrium means that we can set our water potential values, okay, equal to each other. So again, we have the water potential of the cell, and then we have the water potential of the solution. Not only that, we can split it up into its component parts. We have the water or pressure potential plus solute potential equals pressure potential plus solute potential. With a surrounding solution of 0.3 molar sucrose, so that's describing the solution in an open beaker. Just like stated before, an open beaker would be a pressure potential of 0. So that's where I'm going to label. Underneath this equation here, I'm going to label what I have. So that pressure potential on the solution side is going to be 0. And let's reread the other ones. Oh, I see I have a pressure potential for the cell to be at 3, 0.0 bars. And then it's asking us for the solute potential of the cell. But I'm not given the solute potential of the solution, but I'm given the concentration, which means I can solve for the solute potential using the equation as stated before. So let's solve. We have negative, and then that I stands for the ionization constant. The ionization constant can be solved for. We just simply look at the substance that's in or being used in the equation, and that's sucrose. We have to ask ourselves, can sucrose be dissolved in water? The answer to that is no, it can't, so that gets a 1. But what if it can? Right? So say our substance is NaCl. NaCl dissolves into water, creating sodium ion and chloride ion. So those are the two ions that are created, and that gets us I to equal 2 if we had sodium chloride. You simply just add the subscripts up to get this number here. That's the simplified way. It will be different if you have a polyatomic ion, but we're not going to get into that. So back to our problem. Sucrose is 1. So the next variable is C for the concentration. That's 0.3 molar. I'm not going to write the unit out just to save space. I can't fit everything there. So R is a constant. That constant is given to you on the AP Biology formula sheet, so you don't need to memorize it, but it's 0.0831. For temperature, temperature should always be in Kelvin. So it's 20 degrees Celsius plus 273 to get that 293 Kelvin. 293. When I plug it into the calculator, I get negative 7.30 bars. So that's my solute potential. Well, I have everything except for the solute potential of the cell, so I can solve. Let's plug all those values in. So I have 3.0 bars plus my solute potential, the thing I'm solving for, equals 0 bars plus negative 7.30 bars. In order to solve for this solute potential, I simply subtract 3 on each side. And let's put the units there. That cancels out. Let's simplify. And we get negative 10.30 bars. And the answer is C. Okay, we're solving our third one. So this was a problem made on another day, starting off with number 1. At 25 degrees Celsius, whoa, whoa, whoa. Again, temperature, noting I will need to use this equation here. At 25 degrees Celsius, a plant cell containing 0.5 molar sucrose is placed in an open beaker containing 0.3 sucrose. At equilibrium, whoa, so I know to set my water potential of the cell equal to the water potential of the solution. What is the cell's pressure potential? So now, let's split it up into its component parts. Pressure potential plus solute potential equals pressure potential plus solute potential. So it says that we have that 0 there for the open beaker, and it's asking for the cell's pressure potential. We're not given the solute potential, but we're given the concentration for both. So let's solve. I have the cell's concentration, so I'm going to be setting up my solute potential here, negative iCRT. Plugging it in, I have negative. And the sucrose, once again, which means my I is 1, and I have the concentration to be 0.5. I know my constant. And then I have, instead of 293, it's 25 degrees Celsius this time, so it's actually 298. I plug it into the calculator and I get negative 12.38. So I'm putting that 12.38 here, and I'm not done. I need the other solute potential. Remember, you can only solve for an unknown variable if you have only one variable missing. So let's plug it in. Negative 1. This time the concentration is 0.3. And this part is easy because it's the same condition. We just need to look onto the other side to get those variables value. So again, it's 0.0831. Same temperature as well with 298. Plug it in. We get negative 7.43. And I'm going to plug it in there. So I have all of my variables plugged in except for that cell's pressure potential. So let's solve. We have negative 12.38 bars, and again equals 0 bars plus negative 7.43 bars. And with that said, y'all, once we're here, I would simplify it one step further so that you don't get confused when knowing what to do to get pressure potential by itself. So I'm going to simplify it by making the negative join the positive sign there, or the addition sign. And now it is easy to simplify. We simply add 12.38 bars on both sides. And that gets us a pressure potential of 4.95 bars. And that's how we solve this not that complicated problem. It is A. So I hope this helps y'all. Good luck on your exam.